you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T. We have our fourth part of our series on exponential functions. Today we're talking about the natural number that's assigned the letter E. So we're going to be talking about that number and how we use it in exponential functions. The reason for the letter E is it was discovered by a mathematician named Euler. So his last name, he gets the letter for the number. And this is a special irrational number similar to other ones that we've used, like pi, for example. Besides being called Euler's number, or E, it's also frequently referred to as the natural number, because there's a number of phenomena in physics and in science that can be modeled by using this number. What Euler did is he looked at this mathematical expression. Now this looks familiar to part of the compound interest formula. And he looked at what happens as n approaches what's called infinity, meaning he's looking at what happens as this number here and this number both simultaneously become larger and larger. And he noticed and found and proved that it approaches this irrational number, which was given the name so that we could use it. If we just look at that, if I put the here just using x instead of the n, I put his formula. So if we graph it, we can see it starts out with numbers, but then it starts to level off. And if we looked in the table, we can see that as we grow, it's getting bigger, but smaller and smaller. And if we went out to, say, a really big number in the table, let's go out to, say, 1,000. And I don't know, let's count by 1,000s, and we'll just look at what happens. And we can see that this number is leveling off. And again, he approved that it approaches and levels to that one particular number. So that's what the natural number is. Let's talk about how it gets used. So there can be, as an alternative to what we used before, y equals ab to the x, we also now have this exponential model. C is similar to the a in our other model. It's the initial amount. And k is our growth factor. Now in this case, we're not adding 1 to it. So k and also how we tell growth and decay is different. If k is positive, this is exponential growth. And if k is negative, it's exponential decay. And the value of k typically is approximately the percent of change that we were doing in decimal. So if we were growing by, say, 20%, then k would be 0.2. If we're growing by, or decaying by 20%, then we would be negative 0.2. Now, if we use our business terms, P for principal being the initial amount, A for the amount, R being the interest rate instead of K, we get what I call the PERT formula here. That is used for what's called continuously compounded interest. Because if you remember the way Euler's number was created, this number down here, which was the number of times per year the interest is paid, in this case, if we use E, this number is going to infinity. So we are paying interest an infinite number of times per year, or in other words, continuously. So let's look at how that would apply to a problem. Now we looked at this example in part 3. We looked at what happens to this inheritance of $25,000 and what would happen if we saved that for 30 years. And we saw as the number of compounding intervals went up, the final amount. So let's look at the ultimate is we had continuously compounded interest. So if we look at for the 5%, our formula would be A equals, now the principal is 25,000. E, and we're raising that to the RT, so R is 0.05 times T, which is 30. And when we want to do this for 8%, it's going to be the same thing, except we're going to change the 0.05 to 0.08. So let's look at that. Let me bring the calculator over. So here, let's clear our screen here. So now we want to do 25,000. Now you can do the e to a exponent over here on top of this ln button you see here. So I'm going to do second and then that button, and I get my e raised to, now I've got a parenthesis, so now I'm going to put in here 0.05 times 30. And we get $112,000 and $42, $112,042. And if we had the 8%, so let's modify that. Second enter, remember, to edit your amount. And we get $275,579. Now let's go back and compare that to using the previous compound interest. So let's look back at when we did it, say, this was daily. So 112,030 and 275,507. And we can see here when we compound continuously, we get still a little bit more. So in my ancient days, banks didn't have the computing power to use these kind of calculations, so they were computing things on an interest compounding of maybe quarterly, maybe monthly, and then sometimes daily. But now banks pretty much use this compound interest. You can see this formula is much easier to work with than the other compound interest formulas, fewer numbers to plug in, and it's an easier calculation. So good luck with using E and compound interest that's compounded continuously. See you later.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you